The next topic we're going to get into is materials. For the materials section of the morning exam, you'll be required to understand steel and concrete. And by understanding, I mean you have to conceptually know the properties of these two materials and then how to design for them. And so the PE exam will include several conceptual questions that do not require any calculations. And so for these conceptual questions, for the structural portion, primarily they're going to be dealing with materials. However, they can deal with design and to a certain extent analysis. But primarily you may see a question similar to why do you need cover for reinforced concrete? Or why do you need fireproofing for structural steel? It'll be questions like that where there's absolutely no calculations you can do to get the answer. However, it's do you conceptually understand what the materials you're actually working with and why you need to do certain things. So if you notice on the table at the bottom of the page, I've highlighted two values in red. And the first one is the density of concrete, and the second one is the modulus of elasticity of steel. The reason I've highlighted these two is because these are such common values that a lot of times on the PE exam they may not give these to you. They may just expect you to know that normal weight concrete weighs 150 pounds per cubic foot, or the modulus of steel is 29,000 KSI. And it's really one of those conceptual things. If you didn't know, they're not going to tell you, so you just need to know what the materials you're working with are. For other materials, for whatever reason they give you a question about wood, they're going to give you all the values for it. However, these two values, they just expect every civil engineer to know those values. So getting into concrete, as most people already know, concrete is good in compression but bad in tension. So for any tensile forces that are in the member, we need rebar to help support them. And so the other problem with concrete is very brittle. So when you talk about brittle materials, you're always talking about rupture. And so without rebar in there, you could have a concrete beam that will just rupture immediately without yielding. And so yielding and rupture occur at the same time. However, when you start talking about steel is very ductile, so it doesn't have that rupture issue. So once again, normal weight concrete weighs 150 pounds per cubic foot. I don't know how to foot stomp that, so I'll just keep highlighting it red and hopefully it'll sink in, but I don't want anyone to miss that on a test. Primarily the way you see it is they'll give you a concrete beam and they'll just expect you to account for dead weight or for self-weight of the member using this 150 pounds per cubic foot value. The other thing that's unique about concrete is very susceptible to shrinkage and creep failures. So creep failure is basically with a load placed on a beam over time, say several years, potentially 50 years, eventually the material is going to start breaking down and you'll start having more and more strain on the material to the point that eventually it'll become what they call a creep failure. And so that's primarily when they talk about buildings having a 50-year design life. A lot of it is getting at trying to prevent creep failure. However, with creep, most of the way engineers tend to deal with it is by not pushing the material or the member as far as it can go. So if the capacity is 100 foot kips, you don't want to put 95 foot kips on there. You might back it off to 80, 85, and that'll give you a little bit more room for creep. And so I would say creep is primarily more of a concern when you start talking about if it's induced to weathering or if it's induced to high stresses. So concrete also has extreme widespread usage and availability. Primarily the reason for that is it's relatively cheap and most people know how to build with it. And so you can make concrete out of a lot of different things, and if you look at the ACI code, they'll tell you about every type of different ways you can make concrete, and to include even using seawater to do it. So ACI design standards are how we design for concrete, with ACI 318 being the most widely used, and that's the design of reinforced concrete. However, with ACI, just another one of these foot stomping points, ACI only uses LRFD design methodology. So if they give you a concrete beam and you have to do load combinations on it, and you use ASD load combinations, you'll get the question wrong, because LRFD is the only accepted ACI method for concrete. So getting into a little bit more about concrete, this graph just kind of shows you the more water you add to the concrete mix, the lower the compressive strength is going to be. So this is potentially another conceptual question where they say a concrete truck has arrived on site, the driver wants to add water, what's going to happen to the concrete? Just kind of know this potentially. I'm sure Captain Callahan will get a little bit more into that when he starts talking about the construction side of the house, but just kind of conceptually. Kind of another diagram for you, just kind of different ways the different attributes can affect the mix. So you add water to it, you're going to increase the slump. You add water, you'll decrease cohesion, so on and so forth. So you can kind of see the matrix to kind of see how each one of these different variables will affect workability, durability, strength, all sorts of different things. So I just wanted to kind of show you this. If you want to keep this with you, probably not a bad idea, just simply for concrete conceptual questions, this might come in handy. And then here's another table for you. This is just talking about the rebar size. And so if you have a number 3 rebar, you're talking about 3/8 diameter typically, so 3 divided by 8, and that pretty much goes all the way up till about number 9, and then after that it starts getting a little bit different. So this will be come in handy for you unless you have the CE reference book, in which case that one's written in there, or I believe the all-in-one reference book also has this in there as well. So talking about steel, the 3 common types of steel you'll see in structures, see cast iron, carbon, and alloy. Typically for construction, you primarily see carbon steel. And then another part about steels I've already kind of mentioned, steel is very ductile and has a very good strength to weight ratio. However, it is very susceptible to thermal deformation, which is why steel in buildings has to have fireproofing. Because otherwise with the fireproofing, it's going to cause a lot of strain and stress on the material and then cause failure at service loads. So the AISC steel manual is a design guide for structural steel, and the AISC steel manual uses ASD and LRFD. So depending on which one you like, you could use either one. Once again, for this lesson, I'll primarily be talking about LRFD because it applies to steel and concrete. And then one more thing about steel that's kind of unique. For steel, it's not uncommon to have built-up sections. So what I mean by that is, say I have this W shape and I put a channel on top of it, that I technically have a built-up section at that point, or I can have a composite section where I have this W shape and I put a concrete slab on top of it with some actual anchors between the steel and the concrete, so I develop composite action. Both of those would be considered built-up sections, and so with steel you tend to find that more and more, and it just comes down to the steel designer or the steel or engineer of record wants to change some of the properties about the beam, so you can add more materials to it to increase the buckling support for it or the torsional support. It just kind of depends what their goal is for it.